Hello, everyone. I have a quarter past the hour, therefore we should begin our second session of presentations today. Once again, we'll have a combination of scientific papers being presented, a student presentation, and an industry presentation. And so we will have a mix of time limits for those, 12 minutes for the scientific papers and industry paper presentations, and then 8 minutes for the student presentation. We'll follow the order that's in the 4 waves schedule that's listed. And I'm not completely certain who's going to be the presenter in each case out of the number of co-authors, but I'm guessing Christian Schmid, you're presenting our first paper here. So welcome. Once again, we will follow our protocol where we type questions for our presenters into the chat window, and then we'll get to those at the end as time allows. Certainly, then we can also continue discussions in the Wonder networking session that will follow. So with that, let me not take more of the session's time and let me give it to our presenters. So Christian, I welcome you to get started. Hopefully you're able to share your screen. And if not, then Fabiano, I think, will have to be the grantor of permission.
It's done already.
Okay, very well. We can see the PowerPoint. There we go.
Yeah, it looks good. So first of all, thanks to the DSM community, especially to our organizers, the session chairs, and the reviewers, give us the chance to present our work today here. I'm presenting variant value management to optimize complexity and value of product families. It's an industrial case study research conducted from Technical University of Munich, Erlangen Nuremberg University, and the German technology company Voigt. My name is Christian Schmid. I'm a research associate on the Laboratory for Product Development and Lightweight Design at the TUM. I was the academic supervisor of this work together with Markus Mörtel and Professor Markus Zimmermann from our chair. Maximilian Schöber was the on-board student at the Voigt who conducted the work here. And Thomas Luft, our main author, PhD, he works at the Voigt company. He initiated this work and was the supervisor from the industry point of view. Sandro Warzak, professor, is the PhD supervisor of Thomas Luft. So now let me getting started into it. Our short agenda is, I will present and give you a show on the industrial case study. It's a ship propulsion system. I have one slide on this. There arise the challenges which we want to address. And here is our solution, where we want to add a new tool to the big toolbox of DSM technologies. And our tool will be the variant value management. It's a 6 steps approach. I will go in deep into it for every step on a special slide to get a deeper view. And it's applicable in the iterative way. Then I will come to the conclusions where we hit the target and the sum up where we can do further research. So let's start at the case study, the Voigt-Schneider propeller, what it is. You can see here on the left-hand side in the picture, it will always come as a pair of this Voigt-Schneider propellers. The Voigt-Schneider propeller is a propulsion system for ships which can generate thrust in all directions at any desired strength. The special next part of this, it's a vertical axis of rotation with the several blades. You can see here in the bigger picture, this is the blades, and it's rotating on this vertical axis. And the blades are positioned around this vertical axis. The applications, look for the challenges and the economic point of views. The applications where we also create the variants later is in the tugs, the ferries, and the offshore for the ships market. Another point is it's manufactured in a small series, which is also a challenge, and it's a very material and cost-intensive product. So let's come to our approach, where we first start with the challenge. In this market, normally the application drives the customer requirements. The company want to give a good value ratio to the customer and normally responds with a product variant, especially for this market. This will consume resources inside the company. So far, so good. The value ratio is optimized for the customer, but we see another circle here, the red. The more variants we create, the more complexity we add. This will come time delayed, time shifted, and adding more resources and could, by this way, indirectly later lower the value ratio again. So we have here the conflict between value ratio and the complexity on the other hand side, and how to solve this conflict and the problem. We will present our approach for this. Our approach, this variant value management approach, will exactly try to solve this obstacle here with a more deep view where we couldn't find this in other tools, conventional tools before. So we need to create this one new. It's not completely new. The baseline comes from a PhD thesis research from 2019, also from our laboratory, the integrated value engineering, which was based on the product only, product and cost. And we extended this because this study say in the outlook, it can be extended and should be extended to the variant management, and that's what we done. So here is just again this 6 steps. And now I want to start with the modeling, analysis, evaluation, visualization, interpretation, and improvement to show you how we tried to solve the problem, which I described here. Let me start at the first point. It's the modeling. It's a quite simple and easy. The parts of our model is the requirements, the function, and the components. For example, for our Voigt-Schneider propeller, we have on the requirements in different markets, the operational reliability, condition independent on, operation, and so on. We found totally 14 requirements. For the functions, for example, we had a transmit operation, operating information, and so on. Function, we had more. It's around 27 in this system example. And the component level, which derives of assemblies or bill of materials. We have, for example, the blades of the propellant system or the blade drive linkage. This is the start point. Then let's go to the analysis step in our model. Here we can see in the background our requirements, functions, and components. From left to right and from up to down, the same. What we need to do here is to fill 2 matrix. We can see the top down or the bottom up. It doesn't matter because we have seen it's just a mirror of each other. If we have this 2, we can derive or calculate the other 2. This background is the IV technology. And it's also incorporated the actual cost we can see here at the point 14 and the target cost at the point 2. What we added new here is for every variant, one special field where we are weighting the requirements. So the customer or the sales people have to weight the requirement for every application. So we can clearly see the influence on our model and the changes which it's bring. Here we have this a bigger field of a 1 and a 3 and can see, for example, the requirements of easy steering or high position accuracy. We have a pairwise comparison. And we will see, for example, here at the point 2, the high position accuracy is a higher weight than the easy steering in this application. So we have for every application our matrix, which is weighted here for every variant or application with the different values here. But also in the sum, we can see one effect here, it's around the double sum. And here in another application, it's maybe only half of this. So we can first time see the difference and very deep, but also in the top level of this variance. Let's go to the next step, the evaluation. You can see here in the background, it's an Excel sheet, which does the calculation for us. We again have our requirements, function, and components from left to right and from up to down. We can see here is our actual costs, our targets cost row. Here is our main contribution for the variants. Every variant need to have singly these inputs, and then it's come to different outputs in the target and the actual costs. So we start, for example, here at the target cost, calculated this down with the weighting and come to the vector of the requirements target cost, multiply this with the function requirement matrix, which lead us to the function target cost vector. And here it goes down to the multiplication with the component function matrix and arrives at the target cost vector for the components. The same way can be done from bottom to up. And then we have fully fulfilled our fields for the target and actual cost, which we can now visualize, and not only for one product, one variant, but for all desired variant of concern. So in the next step, the visualization is pretty simple. Many of you will know it's a target cost diagram, which we have here. There's a line. Above the line, it's the components, which is, or could be also the requirements and functions, which are too expensive. And under this line is too cheap. And in this methodology, normally we try to bring the too expensive down. And in this box, it's what we can tolerate. So the next step, after we have the visualization for all the parts of our model, this time it's a new, we can compare not only in the vertical, but also in the horizontal way. First time we could see here, which was not able before to see, the same function in different application or variants can really be significantly differing. And by this view, we can first time have also the chance to find the more target measures for what we can do on the functions, components, or the requirements, and by this way improve our system. So let's go ahead. This is our, we call this the variant value management matrix. It's a baseline start for a good overview for the designers to start on their improvements. The next step.
About a minute and a half, Christian.
Yep, I'm aware, thank you. The next step is the improvement. We created a scorecard, which is pretty common in the value management area. We adjusted this to our challenge. We can see here our variant management matrix, and clearly can see our independencies in the horizontal and the vertical direction. We can see our target cost differences and the variance or the application of a concern. We can visualize this and have a very clear documentation and a good base to see what we are doing when we sit on one function and what could happen from one changes in the other directions. And can here with the designers find a suggestion for improvements. Let me come to the conclusions. Our key findings with this approach was the MDM-based approach shows that components, function, and requirements can differ significantly in target costs, thus also in the expectation of the customer in different applications. But also we can see on this basis, specific variance models can be defined for applications where the components do not have different requirements in the different application fields. We can have a uniform design, makes sense here, for example. Let me summarize. Our MDM-based VBM approach supports to optimize complexity and value of product family and variants. It's evaluated in an industrial case study, so you can start and trust, and we are happy if you share your experience with us, the same we do. We gained transparency for target variant measures, and it can be applied to existing and new product portfolios and variants. The last part is, of course, it can be developed further. Let's say go more deeper in the modeling, or the more broader, take more domains inside. Thanks you for your attention. and let me hand over in the right time to the next presenter.
Thank you, Christian. Very, very well done. So you have to stop your screen share, I believe, to allow our next presenter.
Yeah.
There we go. Sjord Nippenberg, thank you for joining us.
Thank you for having us.
Please go ahead when you're ready.
Okay, thank you. So welcome. My name is Sjord Knippenberg from the Eindhoven University of Technology. I'm currently at the Technical University of Munich to join the conference together with Jacob. And today I'm going to present some of my research about the configuration of ship locks using a product platform based on DSM methods. So first of all, yes, what's a ship lock? A ship lock, there are a lot of them in the Netherlands, and ship locks are essential for the transport of waterborne or waterborne transport in the Netherlands. And on the left, you can see how a ship lock works. So when a ship comes at a lock, the gates open, the water level inside the lock lowers towards the level of the ship. Then the gate opens, the ship enters the lock, the gate closed, the water inside the lock is raised, the gates on the other side open, and the ship can continue its way. So ship locks are used to regulate differences in water level, and which I explained just to facilitate the passage of ships from waterways with different water levels. In total, there are 102 ship locks in the Netherlands, and responsible for those ship locks is Rijkswaterstaat. Rijkswaterstaat is the executive branch of the Dutch Ministry of Infrastructure and Water Management, and Rijkswaterstaat is responsible for the maintenance of the main infrastructure facilities in the Netherlands, and one of those facilities is a ship lock. As I just showed, Rijkswaterstaat is responsible for 132 ship locks, which are shown on the map with the dots, red and blue. And around 50 of these locks, which are presented in the red dots, are due for renovation during the upcoming decades. So that's quite a problem to renovate such an amount of ship locks. So the goal of this research is the renovation of the ship locks gives Rijkswaterstaat the opportunity to reconsider current preferences for lock design, so for ship lock design, and B, to investigate the usefulness of a product platform that can be used to support with the renovation of the ship locks. The research method, which I will explain later, consists of 4 steps. The first one is to define the functions of a lock. The second one is a definition of the components that realize these functions. Then the set of feasible configurations for a ship lock is determined. And finally, the feasible configurations for a lock are ranked. So first, the functional structure of a lock. A lock consists out of 45 main functions. And to illustrate the method in this presentation, we have selected 12 functions of a ship lock, which are the main determinants for civil mechanic lock design. And you can see here in the function DSM, so 1 to 12 are functions, and an interface in this DSM can mean a physical adjacency between those functions, a material flow between the functions, an information flow, and or an electrical energy flow. So it's possible that one dot in the DSM describes more than one interface. Yep. And then we're going to the component alternatives for these functions. And for the 12 functions, you can see here in the table on the left of the screen, there are in total 57 components to realize these functions. And you can see on the right of the table, there are for instance, two component alternatives to realize the leading jetty, 3 component alternatives for realizing the leveling system, and so on. And for one function, that's one with ID 8, the seepage screens, there's only one component which can be chosen, so the component is predefined. For 5 functions, which are 1, 7, 10, and 12, the component is selected based on the object-specific characteristics of a lock. And for the 6 other functions, which are 2, 3, 4, 5, 6, 9, and 11, the component is selected based on first the object-specific characteristics of the object of the lock, the choices for other components, and if that's not sufficient, then we need a value analysis to select the appropriate component. So what we've done with the 57 components, you can see here in this DSM on the horizontal and vertical axis, you can see the 57 components. And this is called a component interface matrix. So it shows the interfaces between the components. And the gray blocks on the diagonal represent the 12 functions, and they are numbered with the IDs. And the IDs and the size of the block represents the number of component alternatives that is available to realize those functions. In the matrix, you can see green and white entries. So the green entries, they imply a possible combination of two components. So for instance, between 3 and 4, you can see green entries and you can see white entries. So the green entries denote that those specific components can be combined, are compatible to combine. And the white entries or the empty cells denote that those components, the respective components, are not compatible with each other. And so you can see here the compatible component pairs in this matrix, but that's not a configuration, because a configuration, as you can see here, consists of 12 functions. So also 12 components to realize these functions. And to achieve that, so here we say how to, here it's stated how to find a feasible configuration for the system. And there's an example which you can see here, and it consists of 3 functions, A, B, and C, and 7 components, which are on the vertical and horizontal axis of the matrix, A1, A2, A3 for function A, B1 and B2 for function B, and C1 and C2 for function C. And in this is also a compatibility matrix, and you can see that there are some green entries and empty cells. And a feasible configuration consists of a feasible component pair of A and B, B and C, and A and C. And if you could go through the matrix, you can find out, and you can see this also in this graph. So you can see the black lines there are, you can see that are the feasible configurations of a system, and the dotted lines go towards the 0. So that means that a configuration is infeasible. And for this small example system, you can see that the feasible configurations are A1, this should be a B, B1, and C2. So you can combine A1 and B1, A1 and C2. And here you can see you can combine B1 with C2. And same holds for A2, B2, and C1. And for this small example, it's doable by hand, but for larger systems, we developed an exhaustive enumeration algorithm, and that finds the feasible configurations for a log. To rank this feasible configuration these are found, we followed the value analysis method. It's also described in the work of Paal and Beitz, and that's used to achieve the appropriate configuration for a log. So the first step, we define criteria and sub-criteria to rank the configuration. Next, we assign weighting factors to each criteria and to indicate its relative importance. And combined, a global weighting factor is obtained by multiplying the weighting factors of the criteria below, so the sub-criteria. Next, we score the criteria according to a consistent interval that runs from 0 to 4. And then we combine the score and the weighting factors to calculate a score for each component alternative. So for the component alternative for which we do value analysis. And finally, we combine those scores to score the entire configuration. So you can see here are here's the main criteria, O1, sorry. We have O11, which is then the sub-criteria, and O11 has, again, 3 sub-criteria. And here you can see the criteria that we use. So we use the quality, sustainability, cost, and adaptability, and we added weighting factors to that. For the weighting factors, we did assign those from our own knowledge, but we can think of a sensitivity analysis to find out whether the weighting factors do what they do to the result. And that we also did for the sub-criteria from those criteria. And then you can see here the results, so the weighting factor and the global weighting factor. So that's 0.3 multiplied by 0.4 is 0.12. So that are the global weighting factors of those sub-criteria. So to show that the method works, we conducted a case study for the Spoldersluis, and the Spoldersluis is one of the locks that is due for a major renovation in the Netherlands. And for this lock, 11 functions are considered. As the lock has no salt and fresh water separation system, the lock is located inside the countries and not on the coastal border, and therefore there are no problems with the separation of salt and fresh water for this lock. A total of 35 components are allowed to realize these functions. They follow from the object-specific characteristics of the lock. And these components and their combinations are visualized in object-specific component interface matrix, which you can see on this slide. So again, the green entries denote the possible combinations of two components, and the white entries or empty cells imply that that combination is not possible or not allowed. A total of 30 configurations are found for the Spoldersluis from this matrix, and we ranked those configurations and ended up with here a list of, we showed here the top 5. And you can see here that out of a total score of 64, the first configuration scored 44.8, and then again the second, third, the score decreased quite rapidly in the beginning. So you can see that this score, the best score, is desired for the lock. And we picked the Spoldersluis because Rijkswaterstaat also started with the renovation, and they also defined the renovation scope of the project. And luckily, from our method and the defined renovation scope of Rijkswaterstaat, which took a lot of time before they managed to achieve it, the same configuration followed. So what would be the best configuration for the individual lock? So that's for an individual lock, and to select the appropriate configuration for the Spoldersluis, we need also the feasible configurations of other locks, because we want to apply the configuration not for one lock, but we want to apply it for multiple locks that are due for renovation. And so we want to apply identical component configurations for more locks so they can be reused, and then the renovation would be hopefully easier for Rijkswaterstaat. So to sum up,
about 1 minute, Sjoerd.
I'm at the conclusion, so that's fine, thank you. First step, the configuration of the lock is illustrated for 12 functions of the lock. So we selected 12 out of the 45, and those are the main determinants of civil mechanical lock design. For these 12 functions, a total of 57 components are considered, and those components provide viable technical solutions to realize those 12 functions. The feasible configurations for our lock are found by applying an exhaustive enumeration algorithm, which has been based on the compatibility of the component pairs of the components that are considered. And finally, the feasible configurations of an object are ranked by applying a value analysis method to find the appropriate configuration of that lock. And as I just mentioned shortly, so FutureWorks seeks to extend the method with the configurations of other locks. For instance, by applying or extending the method with a coverage analysis, and I presented coverage analysis during last year's conference. So the next is to combine those methods and to develop a product platform which can support Rijkswaterstaat with the renovation of the locks. And with that, I would like to thank you for your attention, and I hope there are some questions.
Thank you, everyone, for your questions, which we hope to get to at the end. And thank you, Sjoerd, for the excellent presentation. And next presenter, is it you again, or do we have one of your co-authors?
It's not an author, it's Willem.
Yeah, that'll be me.
Oh, excellent. Willem, good to see you.
Hi.
So welcome.
Can
You're up next here.
Can you hear me? Is that all right?
Okay, so 8 minutes. Thank you. Take it away.
Right, just checking again. Can you hear me clearly? Is that all right? Okay.
Sounds great.
Perfect. So good day, everyone. Thank you for attending my poster presentation about my graduation work. My name is Willem, and my research is basically, well, maybe this part is a follow-up on the work of Sjoerd. I focused on developing and applying systems engineering methods to create a product platform for the heads of ship locks. Now, you've just heard from Stuart what a product platform is and what a ship lock is, so I won't repeat those definitions, but they're still on the slides for your information. The head of a ship lock, just to provide some detail, is the part that is within this dashed rectangle. And this includes, amongst other components, the gates and the actuators of the ship lock. And we consider these components in particular because they are quite suitable for standardization in our view, and therefore also for inclusion in the product platform. In the previous presentation, Stuart discussed methods to determine the best configuration of a ship lock, which is, I'd say, one of the design steps in the platform development process on one of the higher levels of abstraction. To fill the platform, we generate various kinds of these design assets, again, on various levels of abstraction, and we would like to capture these assets in some sort of database. Now, one of the topics that I focused on in my work was capturing these assets in formal specifications, that is, specifications that are written according to specific rules or a syntax. We do this to store the assets in a structured manner, a database, which will later enable us to efficiently configure these blocks with less human errors, of course. So going on to the method, how do we do this? We use an existing formal systems engineering language, which is called the Elephant Specification Language, ESL for short, which was developed by Tim Wilskut, who currently owns the company Ratio Case that still develops this language and its associated tools. It has a fixed syntax. The language contains all the constructs needed to accurately specify the design assets and their interactions on various levels of abstraction. The semantics of the language, moreover, enable automatic derivation of interactions within the system, and also allow us to visualize the dependencies within the system in DSMs, product DSMs to be clear. And it also enables us to do consistency checking. So to check whether the interface of a component is compatible with that of another that we specify, but also whether the units of variables that we define are compatible or not. So quite broad. To walk through the process of setting up a system specification or database, like I said, in a general sense, I've defined or identified 3 main steps, which I'll briefly walk through. These are first to identify the hierarchical component structure of the lock. So this is basically creating a component decomposition of the lock that we're considering, or creating a product tree, in other words. The second step is to define the functional interactions or flows within this structure. So for each of the components, we consider the functions that it must fulfill. And we consider 2 different kinds of functions. The first one is goal functions. These specify the goal or function of one component with respect to another component. The other kind of functional interactions is a transformation function, which specifies how a flow is internally converted, so within a component, from the one kind into the other. And using these functional interactions, we already defined part of the interface of a component, of course related to its functional interactions. And then the third step is basically a catch-all step, in which we define all other kinds of specifications, such as design requirements, which you can use to specify quantifiable or quantify certain design variables, or for example needs, which are those specifications that need not necessarily be quantified, or even cannot be quantified, that we want to specify nevertheless. So below I show you a very condensed example of such a component definition defined using the Elephant specification language. And this definition is for the lock complex itself, which is in the decomposition tree, of course, a component on a relatively high level of decomposition, as it is one of the main components. So here in part 1a, we define the component that we're looking at. So again, the lock complex. We then define some parameters, basically the interface. You may think of this as function arguments in programming languages. In step 1b, we define the children components of this component. I've written down a few here. So the UPRED is one, the control system is one. And these then again point to component definitions. And in this way, we create this tree structure of our system. On to step 2, which was defining the functional interactions. The example that I show here is that of a transformation requirement. And this transformation requirement in particular shows how we specify the shipping process that occurs within the lock. We convert a incoming flow of traffic, so traffic in, into traffic out, which is the outgoing flow of traffic. In other words, moving ships through the lock. We also attach 2 subclauses that specify the reliability and availability of this process. And we say that they must be equal to some to be determined value for now. The third example that I show is that of needs. And again, needs are those requirements that we need not quantify or cannot quantify. In this case, that the control system, which is a component that is defined or instantiated up here, must not be placed below ground level to prevent flooding in case of some calamity. If we then define our specifications and our components throughout the system, so if we have all these component definitions and feed them into the ESL interpreter, it can automatically combine them to do a few things. First of all, to check whether the specification that we've written is consistent, so whether the interfaces of the components that we're linking are consistent, do they match, whether the units of the variables that we used are compatible, etc. It also enables us to generate the DSM on the right, of which I'll highlight the benefits shortly. And thirdly, it also allows us to convert the full specification into a formatted document, which contains basically the same textual specifications that I show here, but then in a nicely organized format. And this is typically the document that is transferred from the client to the contractor. The client in this case being Rijkswaterstaat, and the contractor being some company that realizes the lock actually. So the benefits of the DSM are, well, basically the same ones that we normally get from DSMs. So we can use this DSM to verify that the interactions that we envisioned in the textual specification are actually there. So we can observe this or inspect this in a visual way. We can also, for example, identify interactions in the DSM that we did not expect. In that case, we also go back to the textual specification, trace the origin of the erroneous specific or interaction, and then remove it from the specification or correct the error. The big benefit of is
About a minute left.
Yeah, sure. The big benefit of the textual specification document that we've got is that it allows us to the benefit is that it's automatically generated. So what Rijkswaterstaat was previously or still doing is typing out the specification documents by hand. Of course, reusing something sometimes, but of course, in this product platform way of working that we're trying to achieve, we can reuse the same component definitions as we define them here, and then use them to automatically generate this document, which will of course save time. And because of the integrated consistency checking, also saves us errors that we might otherwise make. So in conclusion, by building this library of component definitions, locks can be configured without human errors because we have introduced this automatic process, but also in short time because we're mainly reusing component definitions. This way of working will of course increase the quality of the design. And secondly, a multi-level system specification can automatically be generated and then converted into this human readable document that I talked about, as well as the DSMs like the one that I show here. I hope I give you a clear presentation, and I thank you for your attention.
Thank you, Willem. Very good. I'm going to enter in the chat here our link. Once again, we are having a prize for our best student poster presentation. So please do a sort of vote for that by rating this poster. And I think it's been challenging for me because they've been good so far. so I don't know how to distinguish them perfectly, but maybe at the end I'll have to rethink it all once I've seen them all. But for now, please do your best on this. And also, if you have any questions for Willem, please enter those in, and we hope to come back at the end if we have time. For now, though, we move on to our next presenter. And while they're getting set up, we'll let you do your voting on the Menti page. Han, is this you presenting again?
Yes.
Excellent.
Yes,
Okay.
of course. The only problem is that I have to switch screens again.
All right. Yeah.
Like this.
Okay. That looks good. Okay. Take it away when ready.
Yes, this is a totally different presentation that I did on the data warehouses. This is a very, compared to that, this is a smaller problem. But the interesting thing is that I heard Heidi talking about modeling and DSMs, and the guys from the TU Eindhoven also. And this is a very small example of how we are trying to achieve the same thing. And well, you'll find some interesting insights here. Okay, this is a case by Hering Holland. And Hering Holland is a small company. It only has 40 employees, of which 15 are in production, working in the production center, 10 work for service, and 3 in design and planning. It has it works in a quite a large market. They make Hering Holland makes transportation solutions for, as you see in the picture, chicks, and they create climate controlled trailer systems for transporting those chicks, and they have to be very well climate controlled, because it's very good that if you have 3 days of traveling for those chicks, that the most of them will arrive at the other end in various environmental conditions. Interestingly enough, it's a quite a large market, a worldwide market that needs around or more than 3,000 units a year. So there is potential. And even when you know that there are only 4 companies creating those trailers with a maximum of 30 units a year, it's quite interesting. The way Hering Holland works is not scalable at the moment, so we have to find a solution in the way to enhance the production. So the vision is that the systems are easy to sell, but they want to produce more systems with the same amount of personnel. So they don't want to grow in the number of employees, and they want to double at least the amount of climate controls containers trailers worldwide. They want to shorten the lead time. They want to reduce it from 8 weeks to 8 days. And you can imagine that if you modify a trailer, you have to buy the trailer, have them in the production facility, and then sell it to the customer. So that means that you have 8 weeks of negative cash cycle, which is for a small company not very welcome. So we have to do something, and we came up with, okay, we have to make a modular and more configurable system. On the left side, you see the back end of such a trailer that has the front side of the trailer that has the all the components for the climate control. In the early situation, this was all handmade. So each trailer was configured differently, and now they want to have a configurable setup. That solves a number of problems. You can make your production facility more easy, and you can have several production lines for subcomponents. And if you know what the customers want, you can produce those submodules far in advance. What we try to do is, we started with using a DSM in the first place, but we found out that it's pretty difficult to fill a DSM without the use of another tool. So we came up with the solution of using SysML and Sparks Enterprise Architect and start to model the systems in that way. So here you see the model of the portal, the backside of the trailer, and the colors depict various different kinds of modeling elements. The green part, the green ones are the functional elements, and the orange ones are, and the red ones are the physical elements. And in between there is a layer of virtual components, because that makes it possible for us to define alternatives. Alternative implementation for the same component, the same function. If you model this, then it's very handy to put them in a model structure that has groupings. So we do the component partitioning. We already start component partitioning in the project browser. So we put all the elements in the right spot in the model. And that's an extra step, because if you're going to create a diagram, you can put the elements that you put on the diagram wherever you want them, probably in the area of the diagram itself. To verify if we work the right way and our model is complete, we check that with a DSM. So we import the model into the DSM, and then we can analyze all the dependencies and all the options that are applicable. In this simple DSM, you see the functional decomposition and the first level technical decomposition of this system. And the way you model also means that your DSM is different. The elements on this diagram are the same as the elements on this diagram, though we decided here to use a different way of modeling, and that ended up in a more difficult DSM with more dependencies. So we decided, okay, this way of modeling is better than the other way. The model itself and the DSM is not the only tool in the tool chain. So what we do is we import the model from Sparks Enterprise Architect into Lattice, and from there we put it into Quotes, and Quotes is a configuration system in which you can design and design your configurations. And those configurations are put in the ERP system, so we can do some planning. All the physical components, all the hardware is also part of the list of materials in the ERP system. So we import those components back into the Sparks, so they will become visible in Lattice as well, and we can play with them in the DSM. Well, we had while doing so, we encountered some interesting problems, and I'm not sure if it's a modeling problem or a SysML specification problem. What we found out is that in Sparks, at least, the system, the generalization realization kind, the generalization is depicted by a triangle and a line. is used as the pointing direction. So the direction of this, the relationship between these elements is from bottom to top. But you can imagine that the hierarchy is from top to bottom. So somebody didn't read the specifications of SysML correctly, or SysML doesn't specify a direction in lines. But this means that all those connections end up on the wrong side of the DSM. So we have to fiddle with the DSM to make it workable. What we also notice is that in other cases, the direction and the hierarchy is in the right order. So here is a composition, and the composition goes from the top left to the bottom right, and the hierarchy and the direction are in the same direction. I would have expected that in this situation as well. There are also
a 2-minute warning, Han.
That's okay. Thank you. So simple associations do have an implicit direction in Sparks as well. So there's a 50% chance that when I draw a line between two boxes, it's in the right direction. The DSM tools does not always know the relationship kinds sufficiently enough. That means that filtering in a DSM on specific relationship kinds is not very handy. But what we did find out is that that we cannot use DSM tools just standalone. We started that way, but they are just part of a tool chain to improve your model or your design, etc. Well, since we are a small company, we need some help. I heard some great presentations, but we do appreciate people that want to verify the things that we are doing right now. We are swimming in blue water, and we are not knowing if we are swimming in the right direction. I think we have good ideas, but some feedback would be very helpful. So we like to ask the people in this conference to help us out and do some research or review on the things that we have created so far. That would be very helpful.
All right, thank you, Han.
That's from my end. I hope it's helpful. It's a relatively small problem, but it would be very interesting to find a solution here, because it could help a small company doing big steps.
Very good. And I see in the chat that Mike has welcomed you to reach out to him and given you his contact information.
Okay.
And maybe that's a good opportunity to announce that Mike is our next speaker.
Okay.
I believe. So,
If you're correct.
Mike, Han, you'll have to stop sharing your screen, I believe. And,
I still not. Yeah.
There we go. Okay, there we go.
So you guys should be able to see my screen, correct?
We do. There we are.
Excellent. All right. So shall I just get started, Tyson?
Yes,
All right.
please go ahead.
All right. Well, thanks everyone for your interest. I'm Mike Van Arsik. I'm at SAIC, as my colleague Heidi, who gave the keynote, is also. And I'm going to be talking about some more specifics about how we are using DSMs with systems architecture. And some of this content is drawn from a presentation we made last month at the NCOSI Western States Regional. So, let's get my handy dandy clicker working correctly here. There we go. So we'll skip the abstract. So let's talk about a few definitions. So in our world in defense, modular open systems architecture is important. And a lot of the government programs are continually becoming more and more enamored of this, because they have this need to push their software into more modular microservices with an increased emphasis on sustainability to ensure that the acquisition monster, so to speak, is able to provide systems that are sustainable in the long term. But this means we have to be able to enforce the architecture. I saw a comment earlier about the authoritative sources of truth, and absolutely, if we're not driving our development of the hardware and the software with the architecture, we're in trouble, right? So it's important to make sure that reality mirrors the design. But we have to be able to analyze the modularity for these systems, with the traditional coupling, cohesion, that sort of thing. We do tend to prefer SysML to make our descriptive or executable architectures. It's typically, in our experience, more suitable for this than UAF or UPDM. And I could go off on a class 5 rant on the evils of these frameworks. But for our purposes, let's just take as a given that we prefer SysML. And again, we tend to use the Magic Draw, CATIA Magic tools for our authoring and analysis, as well as LaTeX, which you've seen in a variety of presentations here. So let's talk a little about modularity. So if we pull some discussion from Carlos Baldwin and Kim Clark's book on design rules, modularity is important, and their work showed, and again, this is the best systems engineering book I've ever read that was written by economists. And they talk about how, modularity can unlock up to a 25-fold increase in system value. And because it decentralizes and changes the number and value and location of design options, it allows us to accelerate dramatically the rate of change of a system. And look at personal computers, cell phones, a lot of things that we take for granted have had enormous explosions and advancements due to the modular nature of their architecture, both hardware and software. But they posit that a complete set of design rules addresses the architecture, where we define the pieces of the system, what their roles will be and how they interact with the interfaces, as well as how we go about integrating and testing these. And we believe that our SysML models do address these needs, particularly when they're supported by automated validation rules. And I had provided the link here in the slide. Again, we have a modeling style that we feel is highly efficient, ruthlessly pragmatic, and is focused on elegance. Again, I came to modeling from a non-UAF, non-UPDM background, and I wasn't contaminated by the mindset of, let's make some diagrams to meet our contract deliverables. I've always been interested in solving problems and answering questions, and it's been my experience that the things I need to answer are never on one diagram. They're usually smeared throughout the model. And so these validation rules have grown up as a way to enforce the completeness and consistency of both the structural and behavioral representations in our model to ensure the architecture is meaningful. So how do we go about analyzing that with a DSM? And so we're going to look at two separate use cases here. One is looking at a proposed architecture in SysML, and also we want to look at the evaluating existing software to make sure the as-written code reflects the architecture, because it doesn't do us any good if Heidi and I go off and develop a wonderful architecture. It's cyber secure, it's sustainable, it's all these wonderful things, and the people that actually execute it go do something else, right? So it's important for us to have this round trip with some sort of automation to help us ensure the integrity of the as-built system. And so again, while we're going to focus on CATIA Magic, sorry, was there a question? While we're focusing on CATIA Magic and LaTeX, you may be able to do this with other tools if you decided to. And so again, I will stress that this capability is still under development, and so we're using notional examples throughout this as well. So we want to shift this information to the left. We want to be able to look at snapshots of meaningful metrics, and as Heidi indicated, we're still finding ways to measure those. We're looking to identify unwanted, unnecessary coupling. We want to analyze the system to partition it intelligently and allow these meaningful architectural changes to be made before time and resources are squandered. And we want to be able to factor our code, not have to refactor it. And so again, we really believe that DSMs are a good way for us to look at this. And while LaTeX is wonderful and we like working with them, they've currently been focused on either pulling in existing software code or content that's been properly formatted for input, like through a spreadsheet. And while we can make a lot of custom tables and things in Magic Draw to export this stuff of interest, it's even better if we can just read the native model in either through an API or through like an XML file or something like that. So that's where our emphasis has been as we partnered with them. And so, as we've stressed, the models encode this information about our hardware and software. We end up with this graph database of elements and properties and relationships. And that's, again, where a lot of traditional modeling efforts break down. They don't see the model in terms of the elements, properties, and relationships. They see it in terms of diagrams or give me an SV5 or something. So they're mentally handicapped in some ways from being able to actually exercise the models appropriately because of the wrongness of that point of view. And so We can explore a lot of this natively in the tools, as Heidi mentioned earlier, but they lack the partitioning algorithms and the metrics generation that we can get out of the purpose-built DSM tools. And so we've been working with LaTeX to improve their importer. And as I alluded to earlier in the teaser, not all of the elements and dependencies are useful for architectural analysis. So we've been deciding what information do we retain for these purposes and what can we discard to make the model smaller. Because again, system models can grow very rapidly. And if we can prune out 20 or 30% of the relationships as non-value added, it's just going to lighten the footprint in memory and everything else. So there's benefit to that. And our mutual goal is to adjust the tool so that we get these readable and informative results for the architectures. Now, we can't do that if the model is not well structured. And there was some discussion earlier about how detailed does the model have to be and where do you go? And again, our style and our validation rules are designed to ensure that we end up with a synchronized representation of behavior and structure. And again, we have released these free of charge to the modeling community. And we've also been able to demonstrate some baseline capability of being able to push architectural information and tasks related to software into JIRA, so that if we define a system element with some functions, we can directly push that into JIRA for scheduling in an agile environment. And so again, we're trying to find ways to pull more information out of this authoritative source and share it. Now, I will say this and some of our other papers have talked about this. We really believe that the use of the validation rules is key to be able to generate large models rapidly, even with rookies. And the hypermodeling systems website I mentioned earlier, there were 8 Mars models made there, 8 separate Mars missions done by 40 rookies in like 74 days. And it was thousands of pages of content was exported. So there's definitely a positive impact to productivity and elegance if you use a validation rule like this. So what do we look at typically? Blocks, a system element or CSCI that has functions that own inputs and outputs. We define our interfaces rigorously in our part properties. We have our connectors and object flows that allow us to generate direct or inferred dependencies. If we type something, that's obviously a direct dependency. And again, the state machine's value properties and other elements tend to be of less interest for DSM analysis. And so just here's a look at a system that we had read in where we repartition it. And obviously you can see there's a big impact there. And the nice thing about LaTeX is it makes a work list that lets us capture the sort of changes we'd have to make if we want to approve them. Ultimately, long-term, we'd like to be able to automatically have the tool reorganize it for us, but we're a little ways away from that. Notice here's the SysML-friendly import. So this is using the iconography from the Dassault Magic tools. And so again, this is a lot more comfortable for a system modeler to be able to ingest and look at the DSM using icons that we're familiar with. It just lessens the learning curve, which is quite helpful. And here's a case of where we've been looking at our system model example, which is based on the Ranger lunar probe. And we can see a bunch of its functions, its interfaces, ports, that sort of thing displayed in LaTeX for our convenience. Again, we can use the built-in metrics tools to look at various measures of the architectures. And again, we're still teasing out what is the appropriate metric to look at to evaluate architecture A versus architecture B. But again, this does give us an easier, more interpretable way to look at the code hierarchy and other aspects of the architecture in a nice compact format. So again, here's the case of the Ranger model. And again, as Heidi alluded to, we found out that by having the context separately from the logical architecture, we were actually inducing unwanted dependencies. So we actually moved things around and basically eliminated a separate context package and just subsumed it within the logical architecture itself, which was quite nice. But again, this gives you a sense of the richness of what we can infer from the system model directly. So before and after partitioning, you'll note that it does a pretty good job of breaking things up here. You'll notice that the frame on the right ends up at the bottom because everything else is connected to it. So, logically, this repartitioning of the Ranger makes sense intellectually with what we would have expected to see. And we have things like the propellant tank and other things, segmented because they're feeding into other aspects of the system. So again, the partitioning did do a nice job. And we just took a notional stab at the Ranger.
About
we
a
also
2-minute warning, Mike.
Yeah, I got it. Thanks. I also analyzed some of the student models. And again, they had done some process and product DSMs. And we did some experiments here with one of the 8 models that we referenced. So again, able to extract other types of information out of the model and look at it in that way. So again, we are hoping to find ways to drive our system organization by structural and behavioral connectors. We're still finding idiosyncrasies in the architecture. And again, we're looking for ways to enforce rules that perhaps we have to have functions in the same element, or functions can't be in the same element for redundancy, or that we require or forbid connections, or we may have an off-the-shelf component that can't be changed. So we're still figuring out the rules that we want to enforce with these. As far as the as coded and as architected, again, we want to be able to do this without having to redefine the rules. And again, we are trying to develop this with our friends at Lattice, because again, the problem we have, if you read code into like a tool like Magic Draw, you get something like this, which is really hard to interpret for a systems engineer. And how do we test this against the original architecture and against our earlier work? And so this is under construction, but we're looking at ways to parse out the code and then map it back to the as designed architecture. So in conclusion, well-formed, validated architectural models are of great value to systems engineers and the stakeholders we serve, and looking at ways to apply these adjacent methods like DSMs will give us a lot of insight that we can't get any other way. And again, we feel that there's a lot of value here in communicating software architecture through the DSM rather than trying to use the code reverse engineering into a SysML tool. And again, letting us compare these as written versus intended architectures should help us, from a cyber perspective, and prevent these unwanted dependencies, vulnerabilities, as well as shaping the sustainment and maintenance long term. So thank you very much. And I'd be happy to take any questions.
Thank you, Michael. Much appreciated.
And let's have Heidi go open mic too. She can answer with me as well. So.